This is Reigate College Maths Pure 6, and this video is going to cover parametric differentiation. So we'll cover the examples on page 5 of the course workbook in a moment, but just quickly go through the theory behind this. We met parametric functions earlier in Pure 5. So we've got two functions which are both functions of parameters. So here we've got y and x, which are both functions of t. So what we're going to do then is we're going to think, how do we find dy by dx? We can find dy by dt and dx by dt. We're going to assume that we can do that. So what we do is we use a version of the chain rule. So we're going to say that dy by dx is equal to dy and something over dx. So we simply put dt in at the top and the bottom, dt and dt. So this is one way of writing the chain rule. And then we remember that dt by dx is equal to 1 over dx by dt. So this is now equal to dy by dt times 1 over dx by dt, or it's very common to write that in this way, dy by dt over dx by dt. Try and make sure that you don't get confused by the fraction within a fraction. So try and write dy by dt. You can put brackets there, and then the fraction bar in between. So what we're going to do is we're going to say if we can find dy by dt and dx by dt, we're going to use this. We can find then dy by dx. It'll look a bit strange if you're used to working with x, because this is all going to be in terms of t. So let's now look at the examples on page 5 of the course workbook. So here we've got x equals t cubed, so dx by dt is equal to 3t squared. Y is equal to t squared minus t, so dy by dt is equal to 2t minus 1. So then dy by dx, remember, is dy by dt divided by dx by dt. If you find yourself liable to forget which way up that is, remember that y is on top here, x is on the bottom here, so dy by dx, dy by dt is on the top, dx by dt is on the bottom here. So this is going to be 2t minus 1 over 3t squared. Okay, and just be careful, don't fall into the trap of saying there's a t on top here, there's t squared down there, we can cancel a t. We haven't got a t in this term here, you can only cancel if you factorise. So we're going to leave it like that, and we can substitute values of t into that derivative if we want to find the value of the gradient there. Question number 2, find the coordinates of the stationary point on this curve. Well, stationary points occur where dy by dx is equal to 0. So let's find, first of all, dx by dt. So dx by dt, we're going to need to use the chain rule, dx by dt. We're going to differentiate the outer function outside the bracket, so that's equal to 2t squared minus 3 times differentiate the inner function, so that times 2t, and let's simplify that to 4t t squared minus 3, or we could write it as 4t cubed minus 12t, I guess. Let's find dy by dt now. Dy by dt is equal to 2t minus 4. So now we've got dy by dx is equal to dy by dt goes on top, so that's 2t minus 4 over, this one goes on the bottom, so 4t t squared minus 3. And even if we factorise the top there to 2 times t minus 2, we can't particularly simplify that. There's no cancelling. So, stationary points, dy by dx equals 0. It's a good idea in the exam question to write that out. Makes it very clear that you know what you're doing. It helps you actually. So we want dy by dx to be equal to 0. For a fraction to be equal to 0, its numerator must be equal to 0. So 2t minus 4 equals 0, and that means t equals 2. So at the station point t equals 2, we want to find the coordinates. We're just going to substitute them into the x and y functions there. Substitute 2 in there, we get 2 squared is 4, minus 3 is 1, 1 squared is 1. So coordinates 1, and put 2 into here, we get 2 squared is 4, minus 8, so minus 4. So coordinates of the stationary point are 1, minus 4. Okay, let's go on to question 3 now. So question 3, we've got, this time we've got parameter theta instead of t. It's going to work exactly the same way. So we're going to get dx by d theta this time is equal to minus sine theta. Dy by d theta is equal to, if we differentiate sine of 2 theta, we get 2 cos of 2 theta. So dy by dx this time is equal to dy by d theta over dx by d theta. Exactly the same as we had before, but with theta instead of t. So that is equal to dy by d theta is 2 cos 2 theta over minus sine theta, or we could write minus 2 cos 2 theta over sine theta. Don't fall into the mistake of thinking that this is cosine over sine, so that's cot, because this is 2 theta and this is theta. And what do we want to find? We want to find the equation of the normal at the point where theta is equal to pi over 2. So let's find the gradient of the tangent. So at theta equals, what's it, pi over 2, I'm going to write mt for tangent. So the gradient of the tangent is given by dy by dx. That's going to be equal to minus 2 cos of pi over sine of pi over 2, which is, well, let's see, cos of pi is minus 1, isn't it? Sine of pi over 2 is 1, so this is minus 2 times minus 1 over 1, which is 2. So the gradient of the normal then, mn, is equal to minus a half. And we also need the x and y coordinates to find the equation of the graph. So at theta is pi over 2. If we put pi over 2 in there, cos of theta is going to be 0. So x equals 0, y equals sine of 2 times pi over 2, so sine of pi, which is 0. So it's going through the origin, isn't it? So we've got y equals minus a half x through the origin, so its y-intercept is 0. Okay, so that's 3 examples on parametric differentiation, and now what you should be doing is doing some practice questions from exercise 9G in the textbook. Your teacher will let you know more about exactly what they want you to do.